At the end of the previous lecture, we finished with the PIQ where we're talking about, finding the velocity of the center of mass of two balls. And we reached at Newton's second law for a system of particles. So we said that if we look at the motion of a system's center of mass, then we can look at the position of center of mass, velocity center of mass, and acceleration center of mass. And by extension, if we're looking at the acceleration of the center of mass and we look at the total mass, then we have our net force. F net equals ma, which is what we have been doing all along, just without thinking about it. We said if we have 3 dimensions, then we do the x-axis alone, y-axis alone, and z-axis alone. Okay. And just to recap, we have F net equals ma com, where F net is the sum of all external forces. M is the total constant mass of the closed system. And ACOM is the center of mass of acceleration. Now, why would this be useful? Well, we already know why is it useful, because we have been using it over and over again. But let's look at it in a reverse way, okay, in a way that we have not looked at it before. Now, if I have 3 particles, well, I have a system that's made of 3 particles. They're initially at rest, and there's some sort of external force. Now, each one of these components, okay, each one of these particles will experience the force slightly differently. F1 on mass 4 kilogram is going to be 6 newtons in that direction, so minus 6 newtons. F2 is 12 newtons at 45 degrees. So 12 sine 45 and 12 cosine 45 will give me about 8.5 newtons in each direction. And F3 is 14 newton to the right. What is the acceleration of the center of mass of the system? Say, for example, they are stuck together, they have to move together, and I want to explain in one acceleration, in one sentence, in one number, the acceleration of this system. Okay? Like a human body, I don't want to give you, okay, the acceleration of the head is kadak, or of the hand is kadak, and of the foot is kadak. Just the whole person, this is their acceleration. So I want to find what is the acceleration of the center of mass of the system, and in which direction does it move? Well, we know that F equals ma, F net equals ma. Can you see the screen, by the way, everyone?
Okay. For next lecture, send a new link.
Sorry, say that again?
Can you send a new link for the next lecture?
I can, but what difference does that make?
Some doctors changed the link, and now the problems that were going on, like the blank screen and everything, is gone.
Okay, I can try that. We can try that for the next lecture. I can change the link, and I will change it in Moodle directly. So when you click on it, it will just take you to something new. Okay. Try just leaving the lecture and joining again. Maybe it helps. And we know that F net is the sum of all forces. Now, simple rearrangement. If I want to find the acceleration, I take the net force, I divide it by m, mass. We'll do x-axis and y-axis alone, as usual. X-axis, f1x plus f2x plus f3x. What is f1x? Minus 6. f2x plus 8.5. f3x plus 14. Divided by 4 plus 8 plus 4, which is 12. Someone help me find what the result of that is. And the y-axis, I only have 8.5 newtons divided by 16. minus 6 plus 8.5 plus 14, 16.5 divided by 16. So this is 1.03125. And this will be 1. No, made a mistake. 0.53 meters per second square. So that means my acceleration is going to be 1.03 in this direction, 0.5 in this direction, which means the resultant would be along this angle. My magnitude of the acceleration will be 1.03 squared plus 0.53 squared, then square root, so about 1.2 meters per second squared. And the direction, tan inverse of y over x, will be 27 degrees, so it will be in this direction, 27 degrees. So we took a body which consists of multiple particles, and we are describing it using only one number, only one variable. Now let's do some PIQs. It will be under the previous lecture, lecture 19, section 9.1 to 9.3. Why is it kicking me out? So I'm about to start the PIQs. Just give me a minute to get it up on the screen. Okay, do you see a PIQ or not yet?
Not yet.
Okay, let's see what the reason for that is. Okay, there we go. Now we should be able to see it. Okay, 47 people have joined so far. So we're doing part A first. A girl is sitting at the front of a boat on a still area. The boat is at rest. The front of the boat is pointing north. The girl then walks to the back of the boat. What is the net external force on the system? do a bit.
دكتور لو سمحت البي اي كيو في الموديل ولا؟
في الموديل أيوه.
ما ظهر مع الخانة.
في
ويكتم
تحت الليكتشر الماضي، شوف تحت ليكتشر 19 بي اي كيو نمبر 17 9.1 to 9.3.
اي نعم خلاص حصلت.
ايوه. Okay. Let's see what the consensus is. Ooh, we seem to have a lot of people choosing one option. Now, I don't know which option is that. We will see it together. It is 0. Excellent. Indeed, it is 0 because the girl is acting on the force from the inside. So the external force is indeed 0. Now we go to the next question. Okay. And we'll quicken it up a little bit. Let's go. As the girl moves south to the other end of the boat, will the location of the center of mass change? Or will the COM move? I'm not asking if the boat will move. I'm asking if the center of mass, the location of the center of mass, will move or not. Tricky, but think about it. Okay. Let's see. 34 people still, 21 still, 18. Okay. Ending the window in 3, 2, 1. Let's see. 62 people said no. 21 people said yes. Okay. Okay. Fair enough. Let's do one more. Next. As the girl moves south to the other end of the boat, Now, some of you said the COM will move. Some of you said the COM will not move. Now the question is, what will happen to the boat? Will the boat itself move? Will it move? Will it remain in its place? Will it move north? Will it move south? Think of it. Some of you said the COM would move. If you think the COM would move, do you think the boat would move? If you said the COM would not move, do you think the boat would move? It's not as simple as it sounds, or maybe it is, I don't know. Let's see. "19 people haven't responded so far. 15, 11, closing the window in 3, 2, 1. 3 people have not responded. That's okay. Ooh, we have 60 people saying it will move north, 3 people saying it will move south, and 21 people, so a close contender, saying it will remain in place. Now, here is the girl. When she moves to the other side, first of all, she's just like this, okay? She moves to the other side. Any forces are internal because nothing from the outside did anything to the boat or to the girl. So external force, 0. Now, the boat, when she is moving, will move. Why? Let's take this reference line. The purple line is the center of mass of the girl. The yellow line, or the orange line, depending on your monitor, is the center of mass of the boat. Where's the center of mass of the entire system? Girl and the boat. It will be here, somewhere in between, صح? Right here? In between somehow? Okay. Now, when the girl moves to the other side, when the girl moves to the other side, where's the center of mass of the girl now? The center of mass of the girl has come to the left. So the center of mass of the system appears to have moved somewhere. Right? لكن نحن الحين عندنا مشكلة. احنا قلنا center of mass moves إذا في external force. والحين قبل شوية قلنا ما في external force. طيب كيف السنتر اوف ماس تحرك؟ قبل السنتر اوف ماس كان هنا، هذا الصوب من القارب. الحين جاء هذا الصوب من القارب. لكن ما في external force، كيف تحرك؟ افتونا في 7 سنتر اوف ماسات. Yes, no. For the keen-eyed of you, okay, put a pencil on your monitor on the red line where the center of mass is. حطيته? I'll give you a couple more seconds. حطيتوا قلم؟ انزين ما تحركوا القلم. I will change the slide. ايش صار؟ القلم ما زال على السنتر اوف ماس صح؟ لكن مكان السنتر اوف ماس تغير. صح ولا غلط؟
Yes.
فاللي صار هو there we go. مريم has written it in the chat. تغير نسبي لكن ما تحرك. So what happened is actually the location of the center of mass did not move because there was no external force. But when the girl moves, the only way the center of mass can stay where it is without movement is for the boat itself to move. This is why your pencil is still covering the exact same location, which was the center of mass. So the boat instead moved north. Okay. So the center of mass does not move, but the boat moves to compensate for the movement of the car. Cool? واضحة الفكرة؟ Okay. I'm assuming silence means الفكرة واضحة. طيب. ألعاب نارية. Something that is common في الأعياد الوطنية عندنا. Now, what happens is الألعاب النارية أصلاً هي عبارة عن قوطي صغير صح؟ علبة صغيرة. You launch it at a certain trajectory. You launch it at a certain trajectory up until some point when it explodes. Now, when this thing explodes, we see the whole fancy color show. But here's a question. Does this force of explosion, does it come from inside or outside the canister?
Inside.
It comes from the inside, right? There's chemical inside, or there's pressure inside, or ينبط, or the whole thing explodes. Yeah, it comes from the inside. So if the only force here is internal, what happens to its center of mass?
Remains.
You have things moving all around the place, but the center of mass, if you really look at it, will remain in the same location here, in the center. And even though all of these pieces are going left and right, if you continue to look at this place, okay, and you put it in a computer simulation software, you will see that the dynamics of all this shower going left and right add up to the center of mass still coming down like this, as if nothing happened. The center of mass will continue on a parabolic path, just as it was at the beginning, as if nothing happened, as if it did not explode, because there was no external force. Have you ever noticed that in movies or on news, whenever there is an airplane crash, one of the first things they do is always to seal up the area and look for debris, look for parts. And they don't move the parts. They put all these, cones around it, showing where each part exactly is. Do you know why? One of the first questions that investigators ask themselves whenever there's a problem with an airplane is, was this something that was caused by something from inside the plane or something that was caused from something that is outside the plane. If, say, for example, la samahalla, it's a suicide bomber or a mechanical failure, then it's an internal thing. So the center of mass, they will look at all the debris, put it into a computer software, and when they reverse track it, it will come to the same center of mass. But if it was an external, like an angry flock of birds attacking the plane, and it did happen before, or, say, for example, a rocket hit it from the outside, a missile hit it, okay? Then when you look at these all the pieces, your center of mass will not match. It will be off. Because what happens? If you have a rocket, for example, coming this way, then the center of mass of the system involving the rocket and the airplane will be probably somewhere around here, outside. Yeah? Okay. I will skip through this and introduce a new concept. The concept of momentum. We have all seen our fair shares of accidents on the road. I'm hoping none of you have ever been in one, and I'm hoping none of you ever will be in one. Okay? But we have seen our fair share, even if only on TV. Now, let's say blue car, Camry. Yellow car, Corolla. This one, what's the biggest car you can think of? In my head, it's the H1 Hummer. في سيارة أكبر منها في السوق? That looks like this. في الجي ام سي اللي كانها مال كان شكلها بيك اب لكن ما بيك اب.
H2 أكبر.
H2 أكبر ولا H1؟
H1.
أنا عبالي H1 أكبر وبعدين H2 شوية أصغر و H3 كذا كتكوتة مسكينة. داخلة في العيلة غلط. زين but again I'm not a cars guy so I wouldn't know. Now H1 H2 اثنيناتهم شوية كبار وعمالقة. Okay. Now لما الكامري تدعم في الكورولا ايش يصير؟ قول الكورولا واقفة والكامري دعمتها، وش يستوي؟ أو الكورولا جالسة تمشي والكامري دعمتها. What do you see happening? I'm here all day. ما مستعجل. When someone replies, I can continue.
I think they will get similar amount of damage on each car.
Okay, similar amount of damage. That's one thing. Okay, what about when the Hummer hits the Corolla? الكورولا واقفة أو ماشية في أمان الله والهمر تضربها. وش بيستوي في الكورولا؟
It depends on speed maybe.
Yeah, but assuming it's the same speed. كامري كانت على 100 والهمر على 100. واثنيناتهم دعموا الكورولا. What will happen is الكورولا بتتكربخ آخر كربخة start with and most probably بتطير. الكورولا بتطير بتروح قدام يمكن 50 متر 100 متر كأنه حد شايد كورة. Yeah. Why is this? طيب اثنيناتهم دعموا الكورولا بنفس السرعة، سرعة 100. ليش الكامري الأثر مالها كان أقل عن أثر الهمر؟
Kinetic energy for C is bigger.
Okay, kinetic energy is bigger. Mass is different, yes. Now, When we say kinetic energy and mass, we depend on two things, right? Mass and velocity. Kinetic energy is half mv squared, so it depends on mass and velocity, right? So we introduce something, a new concept. We call it linear momentum. It depends on m for mass and v for velocity. The linear momentum of an object is defined as the product of its mass and velocity. P equals mv, where p is the linear momentum. And it has a unit of Newton seconds or kilograms meters per second. Give me a minute. Can you hear me? My phone disconnected for a minute.
Yes, please.
Okay, cool.
Yes.
All right. So how do we use this MV? Now, a bit ago, okay, first thing first, vector, you are multiplying a scalar by a vector for momentum, which means that momentum itself is a vector quantity. Now, since it's a vector, we can add it using vector addition. P1 plus P2 plus P3 is equal to P net. P is mv, so we have m1 v1, m2 v2, m3 v3. What does this remind you of? قبل شوية لما كنا نسوي center of mass كان عندنا mi xi, بعدين when we differentiated we ended up with mi vi. We differentiated again, we ended up with mi ai, which was the sum of forces, right? So we can look at the velocity of center of mass for a system of particles, multiply it by the total mass, and we get the total momentum. But why is it useful? Now, if my momentum is, mv, and I differentiate momentum, dp by dt, what do I end up getting? What is dp by dt? Anyone?
Force.
It's force, right? Because I get ma. So if I have the momentum of a system, now we can describe this whole, Camry, Hummer, Corolla thing in three different ways. One, kinetic energy. Two, momentum. And three, force. And three, force, right? Now, let's take a look at this. No, you're not supposed to be seeing the answer. Cheat. Where is this? Okay, here we go. Nope, not this question. Nope, it's not there. Okay, let's just do it in the chat. Okay, take a look at this checkpoint in your book. This figure gives the magnitude of the linear momentum versus time for a particle moving along an axis A. Force directed along the x-axis acts on the particle. Rank the four regions indicated, 1, 2, 3, 4, according to the magnitude of the force. Biggest force to smallest force. okay, in magnitude. And in which region is the particle slowing? I'll give you a minute to try it out and put your answers in the chat. Good. Excellent. Pretty much everyone recognized that force is the slope because it's dp by dt. So the highest slope is 1, then 3, then 2 and 4 are both 0. It doesn't matter if you say 1, 3, 2, 4 or 1, 3, 4, 2. And since the momentum in region 3 is decreasing, that means the particle is slowing down. Good? Now, whenever we are holding a ball, for example, yeah, حارس كورة مثلا, حارس مرمى, or baseball, whenever they are moving, if you're into professional football, you will notice something. Whenever they are moving and then holding a ball, they don't just hold it ويخلوا يدهم مكان واحدة. They hold it and take their hands back slowly. Why is that?
يمتص طاقة الحركة.
لكن هو في كلا الحالتين بيمتص طاقة الحركة. ليش يحاول يمتصها على مدى أطول بدل ما يمتصها على طول؟
يوزعها.
عشان إذا امتصها بقوة فتكون مؤثرة جدا، بينما إذا امتصها على أجزاء فيمتص جزء بسيط فقط من الطاقة.
Good. Very good.
عشان ما تبتد الكورة.
So we have recognized something now, that the speed at which we gain the energy or lose the energy makes a difference. إذا قلنا أنه الكرة خفيفة 200 جرام وزنها، سرعتها الابتدائية 10 متر في الثانية وسرعتها النهائية 0 لأنها وقفت. Now I can either stop it in 1 second or in 10 seconds. The difference is what we call the impulse. Now this is a photo of slow motion, what happens when a baseball bat actually hits a ball. Can you see what's happening to the ball near the bat? In this location.
انفعصت.
If I try to trace the ball, I end up with this. مفعوصة الكرة. And we already said that force is the rate of change of momentum, how quickly you change the momentum. إذا أقلب الآية, then dP is equal to ft dt. Otherwise, the rate of change of momentum, my final momentum minus my initial momentum, is equal to what we call an impulse. Impulse, letter J, we define it as f of t dt. Okay, عندك قوة, you have a force, but for how long is this force? Okay, for how long is this force? So write this down and I'll explain it. Okay. Let's go through a series of exercises. Now, these are not in Moodle. I haven't had time to code them into Moodle. So we'll do them in the chat screen. A ball of mass m moves to the right with constant speed v. It bounces to the left from a vertical wall with the same speed v. So initially it's going at plus v, then it's going at minus v. What is the change in the ball's momentum? So what is J? What is the impulse, or otherwise known as delta px? Just type it in. So we have a wall. The ball is coming with velocity v and then hits the wall and then it's going back with velocity minus v. Okay, we have some A's, we have some B's. Okay, we have almost an equal numbers of A's and B's. What did we say J was? J was delta P, which is equal to P final minus P initial. What is P final? M minus V minus P initial was M V. So minus MV minus MV minus 2 MV. The correct answer is A. Okay. Let's say we have a force and this force is being acted on in some amount of time t. Now the impulse, we said, is force times time. Now we have two forces here. Both of these forces give us the same area under the curve. The first one goes up and then back down again. And the other one is a rectangle, constant force. Same amount of time. Which one do you think would hurt more? Purple or blue? The purple one will hurt most because your force level is actually going much higher. Now the area is the same. So the total effect is the same. But the amount of hurt you get is proportional to the impulse. How quickly that force or that energy goes into you or out of you. In your book, you have this example problem. You have a car coming in at 70 meters per second, 80 kilograms. It's coming in at 30 degrees. It hits the wall. Okay, مثل على الشارع السريع لا سمح الله لا تضرب الحافة. It hits the wall and then goes out at 10 degrees and 50 meters per second. What is the impulse on the driver due to the collision? How do we do it? Do we do it using forces? Or is there another way that is better to do it and easier? dV. Okay. Well, we said that J is equal either to integral of F delta T or delta P. It's easier here to do delta P. My final velocity, my initial velocity was 70 at 30 degrees. My final velocity was 50 at 10 degrees. And that means we have components, X and Y. X component, mvx minus mvi. Y component, mvf y minus mvy. We end up with 80, 50 cosine 10 minus 70 cosine 30. And here we will end up with 50 sine 10 minus 50 sine 30. And what we will end up with is, in the X component, we will have J equals minus 910I, and in the Y component, minus 3500J. So what is my total impulse? If I look at the magnitude, 3,600 kilograms meters per second. This is how much force you would feel inside the car if, this is how much impulse would be on you, in the car if you were inside it. Now, how much force is that? The average collision usually is milliseconds. الضربة نفسها takes no more than a few milliseconds. Yes, in movies, it sounds like, it's much more because the car starts screeching and then تنقلب ويستوي فيها حالة حالة. But this is all as a result of the collision, not the collision itself. The collision itself usually takes just milliseconds. What would the magnitude of my average force be during this collision if my J is 3,600? My impulse, we say J equals F delta T. So my force is J divided by delta T. So the force on my body would be 2.6 times 10 to the 5 newtons, which also means I am either dead or really, really badly hurt, because that amount of force on a human body is just crazy. Now, what happens instead? I have another question. What happens instead if delta t is increased from 0.014 seconds, from 14 milliseconds, to only 1 second? So not a huge increase. You're just increasing to 1 second بس يكفي. What would the force be? Come on, people. Okay, less, a lot less. How much less? Yep, 3616 newtons. Now, which one is more likely to hurt you less? 3000 newtons, 3600 newtons, or 2.6 times 10 to the 5 newtons? Can you imagine what we can do in a car to increase the collision time from, 14 milliseconds to just 1 second? I'm just gonna wait until someone decides they want to answer, because I hate talking to myself. I'm just gonna sit until someone gives me ideas. I have nowhere to be.
What is the question, Doctor?
The question is, what kind of technology can you think of that would make the collision last, instead of 14 milliseconds, more, like half a second maybe, or 1 second?
Using rubber on cars, maybe.
Okay, so the rubber would give it a tiny bit of extra time. That's one option, yes.
ممتص صدمات.
ممتص صدمات. Okay, that's another option. So Mariam mentioned something in the chat section. She said نخليها أقل صلابة. Have you ever noticed أنه, especially if you speak to your grandparents maybe, they will tell you something along the lines of سيارات الحين تعبانة. سيارات أول كانت تدعم ولا تتعور شوية بس، الحين شوية دعمة والسيارة كلها تتكنسل. Have you heard this before?
Yes, a lot.
Yeah. Yep. So أنا بعد أول شيء كنت أقول أوكي، يعني أو إن حديدهم أقوى وحديدنا أضعف. Turns out they are actually correct. They are not wrong. Okay. Turns out they are actually correct. They are not wrong. What is actually happening is, let me show you this. Okay. Okay, here we go. There we go. Look at the old car versus the new car. So 1998 Corolla and 2015 Corolla at exactly the same speed, 64 kilometers per hour, but in opposite directions. Okay. Look at what happens on the inside. So this guy has an airbag. This guy, no airbag. The airbag actually increases the time to about 1.2 seconds. So look at the difference between what happens to the old car and to the new car. Okay, that's enough. So what did you notice? What are the differences?
The collision appear much more prominent on the old cars.
Yeah, the old car السيارة ما يصير فيها واجد. ممكن جزء منها يتكسر، بقية السيارة سليمة ما فيها إشكالية، لكن الشخص اللي داخلها هو اللي يتكسر. On the other hand, the newer cars السيارة تتكنسل، السيارة تتكسر أبو أم التكسيرة، but the person on the inside suffers much less damage. So this is what the old car is. Okay. Because the الحديد أقوى, the steel is stronger there, it doesn't compress. So the entire force comes to the human body. So the amount of force is all the way up here. On the other hand, newer cars, the car crashes and crumples for a reason. It is absorbing all this extra energy, kinetic energy, and then it goes to the airbag, and then, you know, it doesn't look much. Yeah, but the difference between 14 milliseconds and 1 second caused by, you know, the crumpling of the car and the airbag, yeah, reduces it to something like this, which is much, much more manageable for the human body. Yes, you would still get hurt, but you would still be alive. Okay. Now, linear momentum, just like energy, is conserved. Okay. I'm not going to prove to you why is it conserved, but I'm going to tell you that it is conserved. Okay, so momentum before a collision must be equal to momentum after the collision. So if a system is isolated, the external force is equal to 0, then my net change in momentum needs to be 0 because there's no external force, which means my momentum is conserved. My momentum before the collision is equal to my momentum after the collision. Okay, if no net external force acts on a system, then the total linear momentum of the system cannot change. Before equals after. Just like energy, it can go from one form to another, from one body to another, but the total needs to remain the same. Let's take the example of a rocket. Now on Earth, if we want to move something, we push against the ground. صح? Newton's third law. I push against the ground pushes against me, the thing moves. In outer space, there is nothing to push against. So how do we move? We use the principle of conservation of momentum. Now, initially, the rocket is not moving. Their momentum is 0 because P equals mv and v is 0, so P is equal to 0. Then you fire up the engine and hot gases and flames start coming at a certain pressure out the back. Now you have a problem. Out the back, you have velocity, you have speed, you have pressure, which means there is a momentum, P equals mv. But we said P before needs to be equal to P after, so my total P needs to remain 0. How is that possible? The only way that is possible is if my momentum of my rocket in the front direction, because it's a vector, cancels out the momentum of the gas in the back direction. So the total is still 0. And this is how these rockets gain momentum, increases its speed in outer space. It ejects hot gases. Salem has mass 45 kilograms, runs and jumps horizontally off a stationary 168 kilogram boat in the Gulf of Oman. When Salem jumps, his velocity is 2.7 meters per second. If we ignore friction, what will the velocity of the boat be? I'll give you a couple of minutes, do the calculation, type the answer in the chat. Okay, so we have a bunch of B's and a bunch of D's. Okay. Most people are doing it correctly. So initially, my momentum is equal to 0 since nothing is moving. Now, Salem decides to m Salem, velocity Salem, plus m boat, velocity boat. and it still needs to be equal to 0. So M Salim 45 times 2.7 divided by mass of the boat is equal to minus 0.72 meters per second, and it has to be in the opposite direction so that the momentum is conserved. If Salim's velocity is positive, this needs to be negative. The number is still the same for B and D, but the direction is different, and the direction is very, very important. Okay. Okay, we're almost out of time. We have 3 minutes left, and I don't want to start a new thing. I don't want to start a new thing in the last 2 minutes. So we can call this a day today, and we can continue at the beginning of next lecture with the topic of linear momentum.